Hello everyone, this is from Team TikTok, and I'm the leader Qi Xianyang, and followed by member Lim Guo Hong, Go Xiu Yan, Yap Su Chi, and Lim Ken Ta. So this is module 1, which is Introduction to Issue in High Performance Computing. The topic related is about what is a high performance computing, parallel computer architectures, key terms and concept, basic definition, models of parallelism, speed up and overhead, capacity computing and Unix utilities, overview and useful command. So what is high performance computing? It's actually doesn't have any clear definition, but it could be computing on high performance computers or computational facilities substantially more powerful than current desktop computers. So in my opinion, a huge number of computational and memory requirements cannot be afforded by a standard workstation efficiently, and the speed is actually the keyword. Next. For the similar concept, there are two, which is the parallel computing and supercomputing. Parallel computing is about computing on parallel computer, while supercomputing is computing on top 500 machines. So this is the examples. We can see that there are few example of supercomputing, which is as shown in the slide. So when we need high performance computing, case 1, to perform time consuming operations in less time before a tighter deadline. I am a bioinformatics engineer. I need to run DNA matching programs, so I did rather have the result in 5 minutes than in 5 days, so that I can say that study ADN sequence contains significant mutations soon. So for case 2, to do the high number of operations per second, I am an engineer of Amazon.com. My website server gets 100 hits per second. So I did like my web server and my database to handle 1000 transactions per second so that my consumer do not experience the bad delays. For information, Amazon does process several gigabyte of data per second.
What does a high performance computer study? So in this part, we'll study about two parts, which is the hardware and the software part. For the hardware part, we'll study about the computer architecture and the network connections. So for the software part, we'll study about programming predicts, languages and middleware. So for the history, initially all the computers were designed for HPC. HPC means high performance computing. So for the HPC, they were all designed with special hardware. The first hardware is the special processors, special memory, and with efficient architecture. All of the HPC are designed with special instruction sets. For the HPC, it's difficult to use because it's machine by machine and it's not portable. As you know, all the computers from early stages are very big in size, and the computers are mostly used in research or in military. Nowadays, specially designed hardware is not as good as using more processors because now in the markets we can get cheap processors, cheap memory, fast network connections, and work together clusters. Shared memory and distributed memory machine becomes more mainstream, and they have many core architectures such as GPU used for computing, GPGPU. The high performance computing almost equals to parallel computing. The hardware speed is also limited because of the processor's clock rate. It consumes too much heat and it also consumes a lot of power. And for nowadays, the hardware they have introduced multi-core processors. For the parallel computing architectures, the first thing that we are going to talk about is the shared memory. For this parallel computing architecture, we have no issue about load balancing. The I/O is straightforward. All memory areas are equally accessible to all. The processor-to-processor data transfer are done using shared areas in memory. It has limited scalability, and it has industry standard OpenMP. And for the second parallel computer architectures, as you see in the diagram, is distributed. It has distributed address space. The processor-to-processor data transfer are done over internal network topology. Yes, impulse memory locality. Yes, high scalability. Yes, load balancing issues, and is not I/O difficult. So here are the detailed image of the architectures that we mentioned above. In this table, we in this table it's shown that here has the top 10 most powerful computers, and is obtained from the website as is shown in the image. Now the top 10 most powerful computers are shown in a table. The table are shown in the image above.
Here is Limgor speaking. The next one is the key terms and concepts. Conventional and serial execution, where the program is represented as a series of the instructions that are executed by the CPU, and also called sequential execution. Parallel execution of a program involves partitioning of the program into multiple executable parts that are mutually exclusive and collectively exhaustive, represented as a partially ordered set exhibiting concurrency. There are several advantages of parallel computing, which is solve larger problems within bounded time, save on more clock time, overcoming memory constraints, and utilizing non-local resources. There are two types of scalable, which is scalable speed up and scalable efficiency. Speed up. Scalable speed up is relative reduction of executed time of a fixed size workload through parallel execution. And scalable efficiency is the ratio of the actual performance to the best possible performance. Basic definition of main classes of computing, there are three, which is high capacity parallel computing. High capacity parallel computing is a strategy of employing distributed computing resources to achieve high throughput processing among decoupled tasks. Aggregate performance of the total system is high if sufficient tasks are available to be carried out concurrently on all separate processing elements. No single task is accelerated. Use increased workload size of multiple tasks with increased system scales. The second one is high capability parallel computing. A strategy of employing tightly coupled structures of computing resources to achieve reduced execution time of a given application through partitioning into concurrently executable tasks. Use fixed workload size with increased system scale. The last one is cooperative computing. Cooperative computing is a strategy for employing moderately coupled ensemble of computing resources to increase size of the data set of a user application while limiting its execution time. Use of a workload of a single task of increased data set size with increased system scale. Strong scaling versus weak scaling. There are the graph of the weak scaling and the strong scaling, which is when we see from the first one, when one weak scaling and one strong scaling, the graph is the same. So when come with the second and the fourth until the eighth, the strong scaling work is lower than the weak scaling. These are the another graph from the for the strong scaling and weak scaling. And the next one is defining the 3C. The first one is high capacity computing system emphasize the overall work performed over a fixed time period. Work is defined as an aggregate amount of computation performed across all functional units, all threads, all cores, all chip, all core processors, and network interface card in the system. High capability computer system emphasize improvement in execution time of a single user application program of fixed data set size. And cooperative computer system emphasize single application, weak scaling. The next one is the term of the strong scaling and weak scaling. The first one is capability. Primary scaling is decrease in response time proportional to increase in resources applied. The second, single job concentrate. The goal is response time scaling proportional to machine size. The third is tightly coupled concurrent tasks making up single job. The second term is cooperative. Single job, different nodes working on different portions of the same job. Job size scale proportional to machine. Granularity per node is speed over range of system scale. Loosely coupled concurrent tasks making up single job. The third term is capacity. Primary scaling is increase in throughput proportional to increase in resources applied. Decoupled concurrent tasks, each of a separate job, increase in number of instances, scaling proportional to machine.
The models of parallel processing. Conventional models of parallel processing. Decoupled work queue covered in segment 1 of the course. Communicating sequential processing. CSP message passing, which covered in segment 2. Shared memory multiple thread covered in segment 3. Some alternative models of parallel processing. SIMD Single Instruction Stream Multiple Data Stream Processor Array. Vector machine hardware execution of value sequences to exploit pipelining. Systolic and interconnection of basic arithmetic units to mesh algorithm. Data flow. Data precedence constraint self-synchronizing fine-grained execution unit supporting functional execution. Shared memory multiple thread. Static or dynamic fine-grained OpenMP distributed shared memory system which covered in segment 3. The picture above is the systematic multiprocessor SMP usually cache coherence, and the below is distributed shared memory DSM usually cache coherence. The communicating sequential processors. One process is assigned to each processor. Work done by the processor is performed on the local data. The data values are exchanged by messages. Synchronization construct for inter-process coordination. Distributed memory causes grand MPI application programming interface. Commodity cluster and MPP, which massively parallel processor and covered in segment 2. The picture on the right hand side is show the distributed memory. The end often not cache coherence. Decoupled work queue module. Concurrent disjoint tasks. Job stream parallelism. Parametric studies. SPMD single program multiple data. Very causes grain. Example software package, condo, processor farms and commodity cluster. This lecture covers this model of parallelism. Speed up. Speed up can be defined for two different types of values, throughput and latency. Throughput will be given in the general form of completion per unit of times. In computer architecture, the common throughput metric is instruction per cycle, denote IPC. The reciprocal of this is CPI. This is a latency quantity because it is the length of time between successive completion or occurrences. The speedup is defined differently for each type so that it is a consistent metric. One of the most common measurements in computer architecture The execution time of a program can be seen as a latency quantity because it is in seconds per program. For latency values, speedup is defined by the following formula as shown in the slide. The S is the resultant speedup, TO is the old execution time, T new is the new execution time. For throughput values, which are also called performance quantities, the enhanced performance will be in the numerator and the original performance will be in the denominator. Notice that speedup is a unitless quantity. This because it is a relative quantity. For example, we are comparing two specific instance of execution. Speedup is only useful when the experimental data is run on the same system, just with the slight tweak for which the speedup test is being run. The formula is where the S is the resultant speedup, PO is the old performance, and P new is the new performance.
Hi, I'm Sochi. In this slide, we will talk about two examples of the speed up. In this slide, we will first talk about the example 1 using execution times. We are testing the effectiveness of a branch predictor on the execution of the program. First, we execute the program with the standard branch predictor on the processor, which yield an execution time of 2.25 seconds. Next, we execute the program with our modified and hopefully improved branch predictor on the same processor, which produce an execution time of 1.5 seconds using the speedup formula S equal to TO over T new, where it is 2.25 seconds divided by 1.5 seconds, and the result is 1.5 seconds. So the new branch predictor has provided a 1.5 times speed up over the original. This is the example 2 using the cycles per instructions. The cycle measure per instruction CPI instead. First, we execute the program with the standard branch predictor, which yield a PCI of 3. Next, we execute the program with our modified branch predictor, which yield a PCI of 2 using the speedup formula 3 PCI over 2 PCI, and the answer is 1.5. We can also perform a calculation using the performance metric instruction per cycle IPC, which is the inverse of CPI. To calculate the speed up using IPC performance instead of CPI latency, which is using the formula, we will substitute 0.5 IPC divided by 0.335 IPC, and the answer is also 1.5. Superlinear speedup. Sometimes the speedup is more than P when using P processor is observed in parallel computing, which is called a superlinear speedup. Superlinear speedup rarely happens and often confuses beginners who believe the theoretical maximum speedup should be P when P processors are used. One possible reason for superlinear speedup in low-level computation is the charge effect resulting from the different memory hierarchies of a modern computer. In parallel computing, not only do the numbers of processors change, but so does the size of the accumulations charge from different processors. With the larger accumulation charge size, more or even all of the working set can fit into charge, and the memory access time reduces dramatically, which causes the extra speedup in addition to that from the actual computation. One example is the reduction of RAM access time. This happens when the working set of a program is greater than the charge size, which executed sequentially but can fit nicely in each available charge when executed in parallel. This leads to my first experience in a shared memory multiprocessor model, and the second experience in a distributed system. Overhead. The time spent communicating between processors relative to the total time spent performing parallel computation is called the communication overhead (C) and is a quantity which depends on both the processor interconnection network architecture and the implemented algorithm. Overhead is additional critical path in time work required to manage parallel resources and concurrent tasks that would not be necessary for purely sequential execution. V is the total overhead of the overload execution. Vi is overhead for individual task Wi, and each task takes Vi plus Wi time step to complete, and overhead imposes upper bound on scalability. Capacity computing and Unix utilities. Combination of common Unix utilities such as SSH, SCP, RSH, RCP can be used to remotely create jobs. To get more information about this command, try man SSH, man SCP, man RSH, man RCP on any Unix shell. For small lengths, it can be convenient to translate the execution of the program into a simple shell script. Relying on simple Unix utilities poses several application management constraints for cases such as exporting started jobs, querying for free machines, querying for job status, and retrieving job results, and etc. There are several performance issues in capacity computing. First one is throughput computing. Second, performance measured as total volume performed over time to complete. And the third is overhead factors. There are 5 factors that will cause, that is, the first one, startup time, input data distribution, output result data collection, terminate time, and the inter-task coordination overhead, not task coupling. And the last one, starvation, which is insufficient work to keep all the processors busy, and inadequate parallelism of coarse-grained task parallelism, poor or uneven log distribution. Thank you.